we're largely going to finish separation methods today. So this unit kind of breaks into three parts. The first part is polymers. The second part is separation methods. That's what we're looking at now. And the third part is analysis of spectrums, meaning mass spec, IR, NMR. You'll start hearing all of that next class on Wednesday. And so the goal is to be done with the actual core curriculum of this unit by Friday. The goal is to be done with the core curriculum of this unit by Friday, which means that a test is going to be looming on the horizon. So you will have a test, and you'll note that I put up the date for it. It's on February 20th. Now, I know that some of you are on senior breakfast that day. Well, guess what? If you're on senior breakfast that day, February, 26th, this college tour, that's when you'll be taking it because the 11th graders are out on college. This is an 11th and 12th grade exclusive class. So the 11th grades will be out on college tour on the 26th, and the 12th graders, at least a decent amount of them, will be on senior breakfast on the 20th. And so just so you're aware, that's how we're going to work it. So if you are a junior, you are taking the test on the 20th, and that would be next week, Thursday, I think, something like that. Next week, Wednesday. No, Thursday. Next week, Thursday, whatever that day is. And then if you are a senior, you'll be taking it the week after on the day that the juniors are out on college tour. And if you're not participating in either of those things, you'll take it at the first available date. So meaning that if you're a senior and you're not going to senior breakfast, expect to take it next week on the second date of the week. Got it? All right. That means that I'm not teaching new lessons on either of those days if you read between the lines. I will not be teaching a lesson on the 20th, and I will not be teaching a lesson on the, I think it's the 26th would be the other date. Those class periods, because so many people, I believe, will be out, will be for either test it, makeup, stuff like that. Or studying for the Olympiad, depending on what you're doing, or an upcoming competition, because we've got several of those this month. Okay, so with that being said, that's the schedule. Let's get to part 4. You will need a calculator today. I know you're so very excited for that. Stefan may agree with you, or with what I say. Do you remember partition coefficients? Do you remember those 2 points that took forever to do? That's what we're doing today at the end of the lesson. So we're going to be going over separation methods. Today we're going to be looking at a process called chromatography. I think I'm trying to access my database of memories, and I can't remember. I don't think we did chromatography in pre-ACE. Did you do the paper chromatography with the M&Ms if you were in the pre-ACE class? Do you remember that? No? Oh, you weren't in pre-ACE. I don't remember doing it in pre-ACE. We may have time next week on a review day. We'll see. To be able to do some chromatography. But I realized when I was looking, I have to go find the right solvent. So I'm going to test my chromatography papers with some different solvents to see if we can get a good separation before I have a lab for you. So yes, Ramon.
I think in pre-ACE we might have heard. I think I might have heard the term M&M or something like that.
You might have heard an M&M, like
Yeah.
the candy.
You said M&M, right?
Yeah, like the candy. Because I did candy chromatography. I've done some years in pre-ACE and not others. I can't remember, but I kind of don't think we did it your year. I go back and forth depending on where we are in the timing, if we do that lab. But if not, you'll get an idea of what chromatography is today. It is a specific separation by polarity. So go ahead and write here, separation by polarity.
Let's science picture begin. Okay, that's one.
Separation by polarity.
M&M.
And so chromatography, like electrophoresis, is one of the separation methods that Cambridge wants you to be aware of. Like I said, I may be able to. It depends. I got to test it first. I may have like a short lab for you next week because chromatography is actually a pretty quick process. once you have everything ready. It either works or it doesn't work. And I'll explain to you what that process is very shortly. But it's a separation by polarity. So we're going to be looking at polar and non-polar compounds again today. So there's a lot of objectives today, but most of them are very fast and informational to get through. And there'll be a lot of objectives next class too, just FYI. So the objectives are going to come in quick. We got a lot of vocabulary today. It says describe and understand the term stationary phase. For example, aluminum oxide on a solid support. Mobile phase, meaning some solvent that's moving. RF value, what in the world is that? And solvent front and baseline. And then it says explain the differences in RF values in terms of their interaction with stationary phase and of their solubility in the mobile phase. Describe and understand the terms, again, stationary phase, mobile phase, and then retention times. This is for, this right here, it doesn't say it, but this is for TLC, which is thin layer chromatography. And then here, this stuff right here is about GLC. And by the way, if you study chemistry, you're going to learn a bunch of analytical methods of different separation and different devices, and they all have a bunch of acronyms. So there's TLC, there's GLC, there's HPLC, and they all stand, there's a whole class called instrumental analysis where you look at instruments and all these different separation and techniques. IR, NMR, we're starting to look at that now. So GLC stands for gas liquid chromatography, which means that something's going to be in the liquid phase and something's going to be in the gas phase in that type of chromatography. And then we're going to learn how to interpret chromatographs, which is basically the printouts of what you get. Okay, and then here, right here, this is the math. I decided to put it, hopefully we have the time to sneak it into this lesson. This is the last major math topic, I would say, of the school year. It is your last K, and it is different than all the other Ks in a way.
This is the last K?
It's the last K, the last capital K. You know, equilibrium constant?
So it can only go downhill from here.
It's the last K, yes.
You
do, but you don't do the math. The math is here. All right, so thin layer chromatography. This is our first one. And there's a lot here. I put a lot here, a lot to go over. Take a look at the little slide that I gave you. I gave you a little slide at your table, and it is a glass, and it looks like a microscope slide, and there's a white coating on the back. And you can touch that. Try not to break it, though. It is glass. And feel what the white feels like.
Okay, chalk.
Feels like chalk, right?
Which one?
Okay, so the white part of your chromatography, this is what we call the solid phase. It is made out of either aluminum oxide or SiO2. So it's made out of aluminum oxide. Don't taste it. And so how do they get this white paste? They mix it with water, these compounds, and they spread it on a microscope slide. That's what you're seeing. The solid on the top. And it actually can come off. So like it is like chalk, like I have it on my thumb right now. It is kind of like that, but I don't think the material is exactly the same. But it's similar. But you'd have to look that up to see how close that is to drywall, if it is drywall. So the solvent, and this is what I was saying. I was looking on Friday, and I had already placed my chemical order, unfortunately. But the solvent, usually the best solvents that give you the best results are non-polar in nature. And so something like a methylbenzene or a toluene. If you don't know what toluene is, that's coming soon. Toluene is this hexane, cyclohexane. But those are more difficult to purchase. And so I was looking and it said that you could also do with acetone, which I do have, but the results would take longer to get. Acetone's a ketone. And so the more polar your solvent is, the faster your spots will separate. And so the idea here is that if you have a mixture, so for example, this is a little piece of paper. This is called a paper chromatogram. So this is paper chromatography. In pre-eighth, I don't think I had you all do it, but some years I do. It's called M&M chromatography, candy chromatography, and you can take and you can separate the colors that are in M&M. So basically your secondary colors, you can separate them into their primary colors. And so that's why I said we may be able to do something with this next week when we have a review day. But if I have a color like black, black is actually a mixture of a bunch of different colors, actually. So it would separate into all the different colors that are in there. And they'll make these different spots. Your different components will separate into different spots that'll travel different distances based on their polarity. So, what?
Isn't it black number just like a dark green?
But it's which is a separation of multiple colors. So it'll separate into multiple colors as it travels up. And so the solubility of your mixture travels based on what phase your stationary phase is, which is in the TLC, that white paste, and what your solvent is. And your solvent here, like I said, is typically non-polar. And typically, if this is aluminum oxide, that's very polar / ionic. So something that's more polar / ionic will stay back on the bottom. It won't travel as far because it gets stuck with the paper, basically, or with the stationary phase. So you've got two phases to be aware of. The stationary phase, this is the phase that doesn't move. This is where your mobile phase will pass over through. So if we were to do a lab with this, we would take this little chromatogram and we would put it into a beaker. That beaker would be filled with whatever the solvent hits. And the solvent would travel up this column, is the idea. And as the solvent travels up the column, the colors will travel up with it, is the idea. And they stop at a certain spot. And so the mobile phase is whatever the solvent it uses that moves up. You can go home and test. If you take a paper and you put liquid in it, will the liquid travel through the paper? Will it move through the paper? Will it spread? Totally will. And so this makes use of the idea that if I have a liquid, it will actually spread up the paper. And so if I have a paper chromatogram, it'll do that very quickly.
Yeah,
And I can also do it with this plate.
I know.
All right. Why does it go up?
Listen, which one are you betting
Why does it travel up? Because the mobile phase, it's usually, if it's non-polar, it's going to travel up anyways because it has a super high volatility.
Have you done this one? That's
But even if it's water, it'll go up. All right, so the next thing you need to be aware of is something called an RF value. And this is a mathematical value that tells you the distance traveled by whatever spot you're looking to identify over the total distance traveled by the solvent. So B right here is the total distance from start to finish of your solvent. And A, the top number, will be the distance by the specific spot you're looking at. The distance traveled by that spot. So A will always be lower than B. You can scan, show, and go. Because you can't travel further than the furthest. So A will always be lower than B here. In order to compare RF values, because you can actually use RF values to tell you what you have, the important things is that you control the temperature and that you use the same solvent because different solvents have different polarities. So your molecules will travel different distances in different solvents. So you have to keep these two conditions the same. Now, what happens is if I'm separating color, like I'm separating the colors in an M&M, or I'm separating the colors in inks, which is something we can do quite easily. Or we could separate the pigments in plants, by the way. So you can do this in your biology class, actually. They use chromatography, and they use it to separate like chlorophyll A from chlorophyll B. And so you can get your different pigmentations through this method. But there are some compounds that don't have color that you would wish to separate, like amino acids. And so what you can do is you can spray them with a chemical which will cause them to form a color, like an indicator. All right, so we're going to take a look and we'll skip this one. We'll try this one, starting with this one. This is actually from pre-ACE. I was looking at some questions yesterday, and although we didn't cover this in pre-ACE, it's something that could have been covered in pre-ACE. 4 dyes, P, Q, R, and S, are analyzed using chromatography, using water as the solvent, which water, remember, is very polar. The chromatogram produced is shown. Which statement about the dye is correct? And you can tell it's pre-ACE, it's multiple choice. Are all 4 dyes impure? Which dye is pure? There's one dye that's pure. P is pure because it didn't separate, right? So you may want to write that down because it doesn't separate. So A is wrong. The 4 dyes contain a total of 8 different substances. And so the idea here is that each different substance would land at a different spot, like would travel to a different overall spot. How many different substances do you see here? I see 1, 2, 3, 4, 5. Because 5 different distances are traveled. So that means that there's 5 different substances. And so, not 8. Is dye R a mixture of P and Q? Is dye R a mixture of P and Q? No, because P is here and R doesn't match that, right? So I guess it has to be dye S is a mixture of dye Q and something else. Is dye S, that's this one, a mixture of dye Q, which these 2 spots line up perfectly, right? And something else that's not there. Yep, so the answer here is B. That's the way to properly analyze it. Let's try another. I think I have another. Yes. All right, so this was pre-ACE. Pre-ACE multiple choice. What does it look like on paper 4 is the question. So the next question is from an A level, paper 4. And it's one that gives you some numbers. Amino acids can be separated by thin layer chromatography. That's using this. This is a thin layer chromatogram. A mixture of amino acids is analyzed using this technique. A chromatogram is shown drawn to scale. And they gave you the ruler there to help you. That's why I skipped the one question because you need a ruler to measure it out. But they gave you the ruler here in this question. The table shows some RF values. Use the chromatogram and the RF values to deduce the amino acid. What's responsible for spot A? What would we do? How can I figure out the amino acid responsible for spot A? So we've got A is here. What other number do we have that we could use? We've got the whole distance traveled, right? So from baseline to solvent front, this whole thing is what we would call little b. The whole distance traveled. And then little a is from here to here. That would be A. So what would be the mass? The distance for A would be 3.5, or approximately, over the distance traveled in total is 5. And they make it obvious what the answer is going to be. So 3.5 divided by 5 is, you may want a calculator, but it's 0.7, which means which of these is the closest? This is leucine. So leucine is how you would answer. And what about spot B? Could we figure out spot B? Spot B is here. So its distance traveled is about 1.5. The total distance traveled is still the same because it's to the solvent front. That's the total distance traveled, how far it goes up your paper or your silica. So 5.0. And so this would be 0.3. Which of these amino acids would it be? use the nitric acid. A second chromatogram of the same mixture is taken using a more polar solvent. So the stationary phase remains the same, but the solvent is more polar, meaning the thing that's going to travel up is more polar. The mobile phase is more polar. What do you think the effect on the overall RF values would be? Would your A and B move more, or would they move less in a more polar solvent? Anybody have an idea? Issa,
Yeah, maybe they move less
what's your reasoning?
because they have to overcome and more attraction.
So I'm going to write something here that you haven't heard me say in probably a very long time. I don't know when's the last time I said this. When we're talking about two things that are soluble in each other or dissolving into each other, we talk about this concept called like dissolves like. And what that really means is that polar substances dissolve in polar solvents. Polar substances dissolve in polar solvents. And nonpolar substances dissolve in nonpolar solvents.
So you need a group of decimal.
Miss,
Yes,
is it like polar solvents? Like polar substances cannot dissolve in nonpolar or
it's oil and water.
okay.
So if I have oil and water,
Is oil nonpolar?
oil is largely nonpolar. Oil and water form two phases because oil and water don't mix because oil is nonpolar and water is polar. Right? Oil is nonpolar and water is polar. And so they don't mix by definition. However, you can, if you stir it really, really well, which some of you may have tested, you can get them to temporarily mix and then they re-separate over time. You can actually add agents to an oil-water mixture called emulsifiers to force them to mix, but there are additional chemical compounds that you would add to make that happen. They do that in food a lot to get two things that wouldn't otherwise mix to mix. Yes, Atzel.
I think it's important, but like, what is oil made of if it's nonpolar? Well, water.
So it is made of fats, and fats are. You may want to take AS Bio because it's macromolecules, and it is made up of. So if I have just a fatty acid, it's made up of glycerol attached to a fatty acid. A fatty acid is like this.
Seriously?
A ton of carbons, like every single one of those end of those lines is a carbon, and then it does have a COOH at the end, but it's actually, there's a ratio of 5:1, meaning that for every 5 carbons I have, I need to have one electronegative group for it to be considered polar. So if I have 50 carbons and one electronegative group, the molecule is considered to be overall nonpolar, even though it has a little polar section. The overall molecule is nonpolar, and you got this little tiny polar part. But the overall molecule is nonpolar. That actually has to do, if you want to delve further, that's why I said biology is where the application of this goes, because if you look into like your cell wall, the lipid bilayer is actually made of this type of stuff. And so it allows certain molecules through and not others. You got your hydrophilic sections and your hydrophobic sections. But that's beyond the scope of what we're covering right now. Yes. You can sketch your own go. Okay, so what I need you to understand is this though. If I have a polar substance, it's going to dissolve in a polar solvent, which means if I have a more polar solvent and the solvent is what travels, the solvent is mobile, meaning that's what's going up, right? Will something that's more polar carry the amino acids more or less? In order to know that, you've got to know something about amino acids. Are amino acids polar or non-polar? What do you think?
Super polar.
They're so polar. They're so polar. Just look at a basic amino acid. It doesn't matter which one, right? Just whatever, right? That's a polar group. That's a polar group. That's one carbon. There's 2 whole carbons there. This is super polar. Amino acids are very polar, generally speaking. So with that being said, can we answer this question for the 1 mark? What's the effect? They'll move farther. So the amino acids move farther as they are more soluble in the mobile phase. In the mobile phase. And so therefore, what would be the numerical value of the RF? Would it be higher or lower? Therefore, what happens to the RF value? Will increase. Because they'll travel farther closer to the end of the solvent front. So that's how you would answer that. Looking through, not my boss. Didn't break.
That's
Crazy. But you saw some of the powder came out, right? Because remember, it's like a paste. It was mixed with water to get on there. So I wanted to show it to you. Okay, so let's move forward. So I've seen in the past a couple questions like this that shows you a 2-way chromatography, which if you have 2 components in your mixture that go up to the same spot with a specific solvent, you would not be able to tell the difference between those 2 parts of the mixture because they go up to the same spot. And so there is a way to solve this issue. It's add a second solvent once the first paper has dried. You add a second solvent, you turn your paper 90 degrees, and then you have the spots travel again in the second solvent. And it basically gives you a different separation, and so your spots can separate. What does this look like? I wanted to show you a question. Yes.
Why does a different solvent lead to the
Because they'll travel just like different polarities.
Yeah, but if they have the same polarity and they move the same amount in a specific solvent, wouldn't that apply to the other solvent?
Not always,
I don't know.
especially for larger molecules. They may be more susceptible to one to the other.
Okay.
So in paper or thin layer chromatography, and actually there's a lot of experimentation here to like see what is the best solvent. That's why I said I have to go into my lab and test different solvents to see what will give us a good separation before I can give you a lab with this, because I have to see what we have and test to see if they work. I know that in prior years I've tried different alcohols, and sometimes they don't really travel very far, like your different spots don't travel as far as you want them to. So I wanted to go ahead and test that. Maybe we can test that in like a lab aid period, like just to see how you can get different solvents to have your spots travel better. In paper or thin layer chromatography, better separation may be achieved by running the chromatogram in one solvent, turning the paper, and running it in a second solvent. We got a chromatogram produced this way. Ring the spot, which was insoluble in solvent 1, didn't move at all. And this means that, like dissolved like, it just didn't move at all with that solvent. It wasn't soluble in it at all. Which spot would it be? Yes. So it says ring the spot. That's the spot that did not move with solvent 1. Because this is where the sample was applied, it's still there. Now, label A and B as spots that were not resolved with solvent 1, but they were resolved in solvent 2. They moved differently in solvent 2. Isa. Yes. So these 2 right here, right? So A and B. Because they moved to the same spot with solvent 1, but when you turn the paper and turn it this way in a second solvent, they did move to different spots. All right, So that's good. And that's another paper 4 question. Just so you know, this is the same 2 marks that drawing those gigantic molecules is. Yes.
Is this topic more featured in paper 5? Because it's
No, it's not touched it. I have never seen this in paper 5. It's interesting that they even give these topics to you, like these very, very, you know, very much college level topics, because you would see these in your college level courses and you'd run them in the labs. They're kind of just giving you a preview of what you would be doing. Okay, so this goes a little bit into the methodology and differences between paper chromatography versus TLC. At your tables before, while you were doing the bow work, I have a chromatography paper here. So the one that's like this, that looks like just a little paper, that's chromatography paper. And the other one on the glass slide, that's a TLC that has been prepared. And so to compare, you can scan, show, and go. To compare, one of the differences in a paper chromatogram is the liquid actually gets absorbed, right? Absorbed, like a paper towel, right? It'll travel up the paper. But with the silicon dioxide or the aluminum oxide coating here, you don't get absorption. You get something called, what's the other one? Adsorption with the D, which means that they stay on the top. The mobile phase stays on top. It doesn't go inside of the paste here. It actually just like, I think of it like a ball that's traveling, like you can see kind of there. It's kind of like the inks are like a ball that travels up. Yes, go ahead. And so they bind to the surface of the solid stationary phase, but they don't go through. Whereas in the paper chromatogram, it's absorbed instead. So that's one difference. Some advantages of TLC. I have never used these before. These are brand new TLCs. I just found them in a drawer. And so never used these before. So I do want to test it out this week. It's quicker than paper chromatography. It can be used on smaller samples. I think I've done this in my actual like chemistry labs when I was going to school. I don't remember it being stressful. I just remember like, you know, putting the inks there and having it travel. And it can be used on smaller samples. So you can, for example, use it in forensics to identify drugs or explosives. And so this would be used oftentimes in an actual lab. Paper chromatography is what you use more in like your middle school, high school science classes. It's cheap, basic, and it gives you halfway decent results. You can get RF values off of it, but it's often not the best because it's cheap. Basic cheap, you're just using paper. Okay, so you can also use, so it's normally described as adsorption chromatography, that D again being important, that your, whatever your ink is not going through, it's staying on top of the surface. You can actually use TLC, I picked this up I think from the textbook, to detect cannabis, THC. In this, you would take your SiO2, which is the stationary phase, and you'd actually spray it with some silver nitrate. And then you dry it. And the silver nitrate allows the molecule to bind to it, which is ionic, so dipolar. But then your mobile phase is methylbenzene, which is nonpolar, so it would travel with the methylbenzene. And then you'd find the RF value, and the RF value would tell you, oh, that's THC or that's not THC. All right, so TLC can separate components of mixtures of components. What do we call the mechanism of separation in TLC? What's just the name of this process? We're separating by polarity, but what's that called? Chromatography. So the name is just called chromatography. So a mixture of propanone and hexane are separated on a chromatogram using alumina as the stationary phase. That's Al2O3. That would be the white powder. And methylbenzene as the solvent. Which substance would rise further and why? So the stationary phase is Al2O3. And the mobile phase that's moving up is methylbenzene. Which one would move farther with the mobile phase, the propanone or the hexane? Yes.
Is it hexane?
Hexane. I heard it from Daniel first. Hexane. Why?
That's much better.
Because the solvent is nonpolar, so a more nonpolar molecule will move with it because it's more soluble in it. Because the solvent is nonpolar, a more nonpolar molecule will move farther. So you could expect, for example, the hexane to be here, and maybe the propanone to be over here. Propanone's a ketone. It's definitely got that electronegative oxygen, so it's not going to move as much. All right, so that's TLC. Cambridge wanted you to know two types of chromatography, TLC and GLC. And GLC, I did use in my bachelor's level classes. It's well, it used to be like a big machine, and you'll see like the design of it shortly. So this we could technically do in class. TLC, we can technically do this in class because we've got the materials for it. GLC, we cannot do in class because you need a specific machine for it. And we're going to take a quick look at it and see what it does. But it's actually the same concept of polarity. Remember, chromatography is always separation by polarity. It's just what everything is that changes a little bit. And believe it or not, like I said, there's a whole class in chemistry dedicated to just all of these techniques. It is called instrumental analysis. So everything that we learn over these next 3 lessons, there's a whole entire 2-semester course actually of chemistry dedicated to this, where you use the different types of equipment. All right, gas liquid chromatography. So chromatography, that is GLC. This is the actual like look of the device. This is the sketch of what it is. This is a chromatography in which your stationary phase is actually a liquid. Your mobile phase is an inert gas. So you have a separation between the liquid and the inert gas. What do we mean by inert? What does inert mean?
There's no movement at all.
It actually means it's unreactive. It's an unreactive gas. It will also be called the carrier gas. So you see it in here. This is from the textbook, an image from the textbook. They call it here the carrier gas. The carrier gas must be unreactive. So it could be something like helium. It could be neon. It could be nitrogen. It has to be some unreactive gas. So either like a noble gas or nitrogen. Nitrogen's cheap. Plentiful. So before I start talking about this makes use of the concept called volatility. What's volatile again? Because that was actually something in the AS class that we went over a lot, but it tends to be something confusing. What's volatile, Isa?
Whether or not it changes phases, isn't it?
So it's the ability to evaporate. And so the idea is that the lower the intermolecular force is, the higher the volatility. And so you may want to write that little note here. Low IMF equals high volatility. So would your carrier gas be volatile or not? Your carrier gas, would that be volatile or not?
It would be like super unvolatile,
It's
right?
super volatile because it's already evaporated. High IMF means low volatility. So high IMF means low volatility. And what that means is your liquid will stay liquid and doesn't turn into a gas really easily. So water, high or low volatility in comparison to a gas. It would be a low volatility because of its high polarity. So the higher the IMF, the less volatile. The lower the IMF, the higher the volatility. They're inversely proportional. And so it's important to note here your stationary phase. So just like the other chromatography, you're going to have a stationary phase and you're going to have a mobile phase. And it's really the interaction between whatever you're trying to separate between the stationary phase and the mobile phase that tells you how far it moves and how long it takes for it to move. And so you take your sample right here. It says you inject it through a silicone rubber. I'm pretty sure that means pipe. Like just put it into rubber piping. And then here, this is your column. And it's a column oven. Why? Because it gets heated up. Why does it get heated up? Because when you heat it up, you're going to turn your liquids into gases. That's the idea, is to turn something in the liquid phase into the gaseous phase, so it moves through the detector and records it, is the idea. And so your stationary phase, which is in the tubing, is a non-volatile liquid here that has a high boiling point. And so that's what your stationary phase is in a gas liquid chromatography. So that's the liquid is the stationary phase. And so you take your sample and you inject it into the stationary phase, see how long it stays there versus how long it takes to come out as a gas. And then your gas is your carrier or your mobile phase here. The moving happens in the gas phase. And so the idea is that solutes that are more soluble. So when I said interact with the stationary phase longer, that means are more soluble in the stationary phase would come out later. Like it would take more time for them to come out at a certain temperature. So the more polar, typically, at least in this situation, be more interaction. With the stationary phase. So the more polar, the more it's going to stay with that stationary phase, and it's not going to go with the inner carrier gas. But it does depend on what they make your stationary phase. So you have to look at the question to see what they tell you about it. And that's going to help you decide what's happening here. And so here you've got a recorder, and this records the time it takes for each component to separate. So I remember when I did this in my university, we separated gasoline, like the gasoline that you get at the pump. We separated gasoline into the different specific molecules that made up the gasoline, because your gasoline is not pure. It has ethanol, it has like a bunch of different fuels, it has octane, but it's not pure, it's a mixture. And so we use this method to separate the mixture to figure out how much of each gasoline that we had, each part of gasoline that we had, each molecule.
Wait, so which is the best gasoline? Like that has a certain, like the most or less of a certain type of molecule?
I mean, there's people that are, that's an argument actually. Some people live and die by diesel. Yes.
How does the recording kind of like
So this is what you're going to see. It's going to give you a different length of time. And that time is measured against known times in that solvent. And so basically what happens is there's a database of, in this solvent, it takes this gas, this amount of time to come out. And so a computer holds that database, and it basically tells you, oh yeah, that's propane. Oh yeah, that's butane. So computers can do most of that. But you'll see a graph that looks like this, and then it'll measure the time of how long it took that gas to come out, and you'll be like, oh, okay, so that took 175, I'm estimating minutes. That must be Penten 2 own. And so it's an important note to know what is retention time. They did say that they want you to know this definition. For a DLC, you use retention time instead of an RF value to tell you what you have. And so it's really just the time it takes for a compound to come out of the DLC to go through the column and come out of the detector. And so that's what we call the retention time. Retention means hold back. Like that word, retention, retain means hold back. So that's what that means here. So this is another example of retention time. I did find this in the textbook. I wanted to share it with you. There are some conditions that should be controlled in a gas chromatogram. You should always use the same carrier gas. If you're using different carrier gas, you're changing the potential polarity, and you're changing like all of the times possibly. Flow rate, it is like how fast they're pushing everything through. Stationary phase, like that means make your column the same thing, like out of the same material, whatever the liquid is you're putting in it, choose it to be the same. And then temperature, choose the same temperature for the whole entire process to occur. And so limitations of this method. So if you were actually doing chemistry with this method, like to separate mixtures, similar compounds, and by similar, I mean similar molar masses, similar polarities, will have similar retention times and may be difficult to determine, like when you have, if you have a mixture that has two things that are really close to each other. And then if you made something new or you have a newly discovered compound, it's just not going to be in the database. So then you'll have something with a time and you're like, oh, I don't know what that is. How could you figure out what that is? I know that's got to be a question on your mind. That's what we learn later this week. How can we figure out what? Yeah, so that's where mass spectrometry and something we're going to learn this week called NMR comes into play. NMR is nuclear magnetic resonance. And then we can figure out, oh, well, what is it that we do have? And then you can figure it out and add it to the database.
So it's like find something new and then like the computer like gets over
Computer just no, computer just like doesn't know. IBK. Like sometimes y'all write on your tests IBK. It doesn't give the sad face that you all sometimes put on your test.
Left is exercised.
Left is an exercise to the scientist,
So left is an exercise to the researcher.
to the researcher. Go figure that out. All right, so there is some math you can do here. I know you're so excited. This actually follows, it doesn't really look like it here, but it is a triangle.
Of course.
These are triangles, and you can use this formula, 1/2 base times height, to figure out how much of your component you have out of the components of the mixture in that area. So this is how you would find the percent composition of your, and by the way, this is area of a triangle, right? So its area is 1/2 base height. And so you can find the percent composition of your gases in a chromatogram by taking the area of whatever gas you're looking for. So A is, what are you looking for? And then taking the sum of all your areas in that mixture and adding them up for the bottom. Now, I've never seen a question, but that doesn't mean there can't be, where they ask you to determine the areas by measuring yourself. All the questions that I've ever seen look like what you're about to. Let's see, which is here, where they give you the areas already, and then you have to use this information to calculate the values. But this could be used. This formula, you definitely want to memorize. But it's just part over whole. The part is the one I'm looking for. The whole is everything combined together. In order for you to be able to do this, your chromatogram must actually show the peaks. You've got to be able to measure them. The components, all components must be separated into the different components. And the detector must respond equally, meaning that it doesn't have like a mishap. All right, so let's take a look at a couple questions. How could we be assessed on this standard, given that we're not actually going to run a GLC ourselves? We don't have that equipment. You're not expected to have that equipment. So here's what they give you. An aldehyde, an alkane, and a carboxylic acid, all of similar volatility, are mixed together. And then that mixture is analyzed in a chromatograph, and they give you this information. They tell you the separation of the compounds depends on their solubilities in the stationary phase versus the carrier gas. And they tell you what the stationary phase is. You should underline that because that's a really important part. You have to know, well, are these gases going to be, or are these liquids going to be maybe soluble in this, or are they going to go with the gas quicker? Complete the table to suggest which compound is responsible for X, Y, and Z, and give reason. It says, explain your answer, referencing intermolecular forces. How nice of them to tell you that. We want you to answer that way. All right, so it says the separation of these compounds depends on their solubility in the stationary phase. That's a repeat. I repeated that. Complete the table to suggest which compound is which. What are my three possibilities again? It says we have an aldehyde. What else do we have? An alkane. And what else do we have? carboxylic acid. Now, they did not tell us the exact one that we have. They told us that they had a similar volatility, so you can assume that their molar masses are in a similar area. So it's not like one is like 100 carbons and the other's 2. They're similar, is what they're saying. Similar enough you can compare the functional group to make your decision. And so, what is an aldehyde again? Because you have to know what the structure is in order to answer this question. That's all.
It's just like a double O bond at the end of a molecule, right?
Yeah, so that's aldehyde. So I'm just going to sketch that out just to remember. That's an aldehyde. Alkane, what's that? Ethyl?
It's like a carbon group where there aren't any double bonds between carbons.
So just carbons and hydrogens. And carboxylic acid. Go ahead. Do you have it again? Carboxylic acid? Yes.
Well, yeah, I don't know how to describe it though.
CO,
Double bond O and OH.
C double bond O with the OH. All right. So the question is, which of these would stay back the longest and which of these would come out first? Because the way that this works is the lower the time, the faster it comes out. So what would be X? What would come out the fastest? The alkane. So here the organic compound would be the alkane. And what would the reason be? So alkane is the least polar, which means it would be the least soluble in an alcohol. So it would go with the carrier gas fastest. So the idea is that X is the least polar, not attracted to the alcohol, right?
I mean, so the less it's like soluble inside, it goes faster.
If it's soluble in the stationary phase, it goes slower.
Oh, okay.
Soluble in stationary phase means it's stuck in the stationary phase. Like it's stuck with something that's not moving. So it's not moving, if that makes sense.
So if it's like it goes slower.
So soluble means stuck with the stationary phase. It's gonna go slower, it's not gonna come out as fast. So the more soluble it is in the stationary phase, the longer it's gonna take to come out. The less soluble, the faster it comes out because it's not stuck with that, it's moving with the gas. So X is the least polar, not attracted to the alcohol. So then the way that they want us to describe it, they wanted us to say intermolecular forces. So what's the intermolecular force here? So X has ID forces or dispersion forces, and we'll move the quickness. So I'll have the lowest retention time. All right, so then what would be Y? Aldehyde. And so it's actually the only reason you have to say is PD forces, like literally in your explanation. You just have to say PD forces. That gives you the mark. So I'm just going to say the minimum now. And then, because I did a full explanation for the first one. And then the last one must be carboxylic acid. That would be the one that stays with the alcohol the most, right? So carboxylic acid. And it's due to hydrogen bonding. So it would stay with your stationary phase the most. It's the most soluble because it's the most polar. And like dissolves like is that key idea here, that things that are polar will stay with other things that are polar. And so that's how questions would look. That's only worth like 2 marks, not a lot of marks. All right, so there's more to this question. The next part. Same question, I believe. This time they give you the areas of these triangles. They're not perfect triangles, to be fair, but they're like, you know, close enough. You can estimate it's a triangle. I mean, if you wanted an exact area, you could do the integration. But typically, they don't do that. They just are like, 1/2 base height. Like actual real practicing chemists don't usually do the integration. They just do the half base height thing. And they're like, yeah, close enough. And so they do it for X, Y, and Z, and they find that the area of X is 19, the area of Y is 32, and the area of Z is 47. And they tell us that that area is proportional to the mass of the respective compound, and they ask for the percentage by mass in the original mixture of the compound responsible for Z. So how could we figure out this information? So we need that percent composition. Go ahead.
47 divided by 19 plus 18 plus 47.
So the percent of Z would be 47 at the top, because that's the one I'm looking for. And then just add the three areas on the bottom, which is 19 plus 32 plus 47, which is 47 divided by what number? I want to say it's 98. 98, okay. So my brain was halfway working. And then multiply that by 100 to get that to a percentage. And they do want three significant figures here for your final answer, 48.0%. You don't have to write the percent after because it already says percent there, but you can. Okay, so the next slide is informational, and then we get to go to the math that I know you're so excited for. GLC uses. So what do people actually use this method for, like IRL in real life? It's often used for testing steroids in athletes. It can give you separation of steroids because they tend to be nonpolar. It's used to test fuels in motor racing, to test like the components of the fuels that they're using, making sure they're not using anything unauthorized. And it's actually also used for medical diagnosis of blood samples. And so with a sample as small as 1 milliliter, 1 centimeter cubed, you can actually get a good percent of dissolved gases like your O2 in your blood. So I don't know if any of you are working on that astronomy prompt for STEM challenge, but that's an interesting note on that. All right, so then GLC, we usually combine it with mass spec. And by the way, usually these devices, they make like combination devices. They feed one device into another device, and then you have like this one big device that tells you all this different information. So you'll have like a GLC-MS is what they'll call it. And so basically the GLC separates your it separates your gases, and then the mass spec tells you, okay, so this is the molar masses of the gases that I have. So you can use that information to further figure out what you exactly have in your mixture.
It's like ultimate chemistry.
It's what? Ultimate chemistry, yes, when you get all the devices. This is a 1-mark question. And I wanted to make sure to show you what some questions could look like. Thin layer and GLC can be used to analyze mixtures. Each type makes use of the stationary and a mobile phase. Complete, what is the stationary phase of a thin layer chromatography? So what is this? They expect you to know what this white stuff is. You can either say alumina, you can say Al2O3, which is what alumina is, or you can say SiO2, silica, or SiO2. So you could say Al2O3, alumina, or SiO2, silica. So one of those two. Or means one or the other. Yes.
So which one is this one made out
Silica. Mobile phase, GLC. What is the mobile phase? It says with an example. So you can't just say gas. O2 is reactive.
Is it benzene? Oh yeah, N2.
N2. Or like neon or helium. It has to be an inert, unreactive gas. So I would choose either a noble gas or nitrogen, which is got the strong triple bond, so it's unreactive. Yeah. Nitric acid. Nitrous acid? For which one? For this one? Well, it's an acid, so it wouldn't be a great carrier gas.
Because like nitric acid, like it has like 2 oxygens. It's not active. Well,
That's reactive as well. It has to be unreactive by definition.
It's like using cars, like legitimate stuff.
I would not do that. I would not use that for this purpose. Not for this purpose. Let's try another question. Unknown amino acid, this is paper 4, is analyzed using thin layer chromatography. To me, these standards are not difficult. It's just remembering that you have to know this for the test. None of the questions are crazy, but it's informational, which means there's more to know. They give you 2 chromatographs, and they give you 2 different solvents. Can you identify the unknown acid given this information? Do you have enough information to figure out the unknown acid? In solvent 1 and solvent 2. This is my unknown. In solvent 1, it moves here. So according to this first chromatogram, what could my unknown be? What could it be? It could either be Q or S. It doesn't, like, you're just trying to figure out which letter it is. They're not telling you exacts. So here this tells us it could either be Q or S. One of those 2. Because it moved as far as Q and S. So these right here are references. So it's basically like, think about it like this. Have you ever seen like a cop show and they're like, they got like a lineup of criminals and you're trying to get the witness to identify which one is the actual criminal? Literally, that's the thing. This is your unknown, right? And it's one of these 4. And it's based on the distance they travel, like to match it is the idea. This is kind of how you think in forensics, by the way.
I understand.
Trying to match it. So that's the first one. It says it could either be Q or S. So like, suspect. If you think about it like that, it's like suspect P, suspect Q, suspect R, suspect S. We don't know what they are, but we're like you. That's the first thing I saw. So it's one of these 2. And then you can think of it like the solvent 2 is like your second witness, right? Your second witness sees the different ones. It's just they travel different distances. So where does the unknown amino acid fall for solvent 2? R S, right? So both of them identify that it is S. So the answer is S. So S, because it matches both solvents.
Oh, yeah.
In solvent 1, the unknown amino acid traveled as far as both Q and S. In solvent 2, the unknown amino acid did not travel to the same place as Q. It traveled to the same place as R and S. In both of them, only S was the same. Yes?
Oh, yeah.
So it's like matching to see how far it traveled in the different solvents. All right. Do we have enough time is the question. I think we don't. You know why? This was originally going to be a next class's lesson, and I was like, can I move this to today? Because I didn't want it to be a next class's lesson. But, there's also donuts on the line today, and I don't think I can explain this whole math thing to you in 7 minutes. So we're going to have to stop here and do this on the original schedule, which is on Wednesday. So math on Wednesday. So I've got donuts. Unfortunate. What? The fortunate part is you get the donuts.
Okay. For some reason, I always got the red donut.
I mean,
All right. So we're gonna work from the back this time. So Jaden, Shahada, and Omar, come on up. You get first pick.
Guys, don't get chocolate. Guys,
It's a month of
they have like a little.
Grab a napkin and grab a donut.
Guys, I left the comment on a video and I got the bite.
All
All
right. That's row 1. Row 2. Come on up. Row 2.
I'm sorry.
You look
Two
at that.
donuts.
That's a reference.
Are those so?
These are filled. One of them's brownie batter. I don't know. They're like different Valentine things. No risking your donut.
I'm very worried about the fact this is the last cake we get.
Last cake.
That implies that there is no more equilibrium, which is very scary. Why would that happen?
Well, we're into organic and out of.
I got sweat. Like, look at these people fight, and they're fighting each other. That's like throwing people in fight. Every time we
Okay. Take one. Alrighty. Row 3. It is your turn. Row 3.
I don't know if you're right.
Yes, yes. Get
What are they fighting? They just think.
enjoy your win. It's a W. Welcome. The donut from donut row 3.
Reading comprehension curse strikes again.
Reading comprehension usually is the worst. I don't know.
They're just fighting each
It
other.
might be a yeah, I don't know.
Six more people like
So,
It's so powdered.
Thank you.
Right?
you're welcome. Row 4. Row 4. Your turn.
The first one there, bro.
Go ahead.
I know.
Grab a donut. Oh, I don't know about that. There may not be anymore.
That's the only.
That's a brownie batter, I think.
Oh, yeah.
Oh, that could be a jelly. That could be a jelly. That could very well be a jelly.
Think I'm gonna eat chocolate.
Just look at it.
No.
There's only one more filled donut. I think it's brownie batter.
Brownie. That sounds good.
They didn't do a great job with those this morning. They had like new employees. You can come back later and check. Brownie batter. They have new employees. They were training at Dunkin' this morning, so they didn't know what.
Bro.
Yeah, at least I'm next. Wait, is it 5 yet? Why is it roll 5 now? After these people.
Oh! Is that just chocolate?
You still use that.
Chocolate flakes.
Yeah.
Chocolate.
I literally like had I found
All the chocolate.
like my old one of that like in a drawer, and my dad was like asking, "Oh, do you guys use it?" I'm like, "No." So much please.
This one's my favorite. I like maple and I
So much one.
all right. So row one.
Yay.
I bought an extra thing. So
You can get from
still
here.
plenty to pick. Yeah, you can pick from any of the 3. Here's a napkin. Enjoy. You deserve it.
All that and maybe.
Remember your
Daniel.
donuts are getting so late. They don't use them up. Have you seen the price of donuts?
This is what's in aisle.
Are you ready for that? For like your
That's maple. That's
I just like it only
for chocolate return.
no, this one.
Which one's this one? Just
You have
regular.
to come and check later.
Daniel,
Yep.
are you ready?
The one like after school. Lunch.
Are you ready for your red donut to return after the end of this year?
Oh, that's that.
You're welcome.
Yeah.
I refuse.
Stefan, come on up for all your help.
Like you're gonna go like try to get donuts like just regularly, and they're just gonna be like, "Oh, sorry, we're actually all out of donuts." I mean, we had these red donuts, so yeah.
I have never once had the misfortune of ending up with a bread donut in this class. It's amazing. I had this thing for all of middle school. When I got donuts, I'd always end up with the bread one. The one just tastes like bread.
Brett, you mean this?
It was the curse of the bread donut. That one exactly, the curse of the bread donut. And never once has it happened in chemistry, and I'm so happy about it.
Is that one?
It's not a terrible donut. Some people prefer it.
Who likes the bread? I've never met anyone who is like, yes, I'll take the one that tastes like
Coffee.
bread.
You dunk it in your coffee.
Go get bread.
You need me to sign a field trip form? Yeah. Is it for the thing? The thing on the tour. So you understand how I'm working those class periods, right? You see how that's going? Because this is field trip season, so yes. The good news is I won't be teaching a lesson that day, so
Very good.
so you should be very
Now we have
happy
to
about
convince Mr. Morales to also not teach a lesson that day.
Oh yeah.
I mean, I was trying to get ahead by teaching this, but like I was like, you know what? It didn't happen.
Really cool.
But at least the other part got pretty fully explained. So, but I can't rush this because you'll see. You'll see.
Oh.
Actually, can I?
But
Do I have it? Let me show you. I just typed all the questions yesterday.
They're gonna be flown out
So
to New
it's
York.
gonna like this.
Oh.
It's a double fraction, like
I
a
guess
slow
visual
fraction.
I hate seeing it so much
Yeah.
that I just write the reciprocal and I multiply.
Yeah, I mean, I do that. Like, if you see it, I do flip it, but I have to show like how the formula derives. Like, yeah. Here you go. I don't know who this is, so have fun. Have fun. Enjoy your donuts. You've got 10 minutes for a brain break until we go to the next class. This homework's due on Friday. The one from last class is due next class. I'm lagging one behind to give you some extra time.